Hello and welcome. My name is Mark O'Connell. Today I'm going to talk to you about conditional visualization in statistics. This is joint work with my thesis supervisors Catherine Hurley and Katerina Damian. So we'll start with a brief justification for our interest in conditional visualization. We'll briefly discuss what conditional visualization means and then introduce the condvis package in OR. Next, we'll briefly mention some of the existing approaches to conditional visualization. The main one we'll talk about is Trellis, which dates from the mid-90s. We will then move on to discuss our approach to the problem, using interactive graphics in the Convis package. So this is it. If you're going to fall asleep in the next 5 minutes, this is the one bit you need to hear. Our approach is to interactively choose one section at a time, to visualize where fitted models intersect that section, and to visualize data on or near the section. It may not be immediately obvious, but most supervised learning problems can be considered an attempt to infer something about the conditional distribution of a response given some predictors. This point is made in the second section of Hasty, Tibshirani, and Friedman's Elements of Statistical Learning. Usually this means getting some function that maps predictors to fitted responses. With one predictor, we can visualize this function quite easily and see exactly how we have conditioned the response on the predictor. With two predictors, it's not straightforward, but it's possible to produce a contour map or perspective plot of the function. So with more predictors, what do we do? Well, I might suggest that you use the condvis package to produce lower dimensional sections of the high dimensional regression surface. So what do we mean by conditional visualization? In a geometric sense, to condition means to take a section. Here we have a little toy example with the MT cars data in OR. We have a model relating miles per gallon to weight and horsepower. If we want to see the modeled effect of weight given horsepower is equal to 200, we take a section at horsepower equal to 200 and visualize it. You can see taking a section allows us to reduce the dimensionality of the plot. Note as well that there are no observed data points on this section. This is undesirable because we like to see the observed data to see if it supports the fitted model well. When conditioning on continuous variables, most sections contain no data whatsoever, but maybe we'd like to see some data that's near the section. I have written the Convis package in OR to interactively visualize these sections. It is built on base graphics, which is kind of unusual. The main motivation for this was to keep software dependencies to a minimum. Another advantage is having direct access to many of the statistical graphics already programmed in OR. The interactive graphics are also offered in Shiny, but mainly serve as an alternative for people who struggle to install dependencies. This method of conditional visualization works in theory for any fitted model that can be calculated, but in OR it depends on the generic predict function. So if that works without any messing around, it should work without any problems. Here is an overview of how the package is used. Basically, we start with a dataset and a fitted model in OR. Then we call the main function in convis, which is ceplot. We can specify some options at this stage. The predictors we want to investigate, the predictors we want to condition on, the type of plot, separate windows, or a Shiny web application. So this function produces a plot. We can then interact with the plot via visual summaries of the conditioning predictors in order to choose sections. And every time we pick a section, the visualized section is updated. So let's look at an example now which shows the importance of conditioning and gives us a brief look at the condvis package. The first dataset we'll look at is the FEV data relating lung health and smoking in children. This comes from a paper on statistics education and makes useful material for basic discussions on conditional relationships. The response is forced expiratory volume used as a proxy for lung health, and the predictors are gender, age, height, and smoking status, which is binary. So we'll start with a fresh OR session. We include the condvis package. We include E1071 for fitting a support vector machine, and the FEV data are in the covreg package. So we just do a little tidying of the data first. Now, on producing a box plot of FEV versus smoking status, we see something surprising. The marginal distribution suggests that smoking is associated with better lung health. So we continue by fitting a model, kind of just for illustration purposes here. So we fit a support vector machine. So we call CE plot, and our predictor of interest in this case is the smoking variable. So looking around a few sections up here, we see something more sensible. The model would suggest that smoking is associated with lower values of FEV. But if we look down here, we see the same sort of problem arising again. The model seems to suggest that in this area, that smoking is associated with higher FEV values. But if we look at where the section is over here, we see that these are kind of 6 or 7-year-olds. And then if you look at the section, there are no smokers near this section at all. So essentially this is a kind of an extrapolation in the data space. So the message here is that flexible black box models are just as capable of misleading analysts as more rigid linear models. A good way to combat this is to drill down into the details and look at sections and examine how the data near the section support the fitted model. Now, this is just a quick look at 3 existing approaches to conditional visualization. This is more for people who already know what these things are. It's worth noting at this point that trellis does not depend on a fitted model. Partial residual plots depend on a fitted additive model, and ice plots need a fitted model, but it does not need to be additive or analytically simple at all. Any function mapping the predictors to fitted values is acceptable. For this presentation, we'll concentrate on trellis. Trellis produces individual plots for subsets of the data. These subsets are defined by intervals on the conditioning variables. So each panel below here represents data falling in one of the intervals above. Let's talk about 2 ways of thinking about trellis. The first way, we take a section at each observation in an interval and then place all of these sections on top of one another in order to make one plot. Another way to think about it is to take a section at the centroid of the interval and plot points which are a certain distance from that section. We'll talk more about this later. So now, what's our approach? We look at one section at a time. We choose each section by interactively clicking on familiar visual data summaries in OR. We then visualize the fitted model where it intersects the section and show observed data points near the section. We give a little more meaning to near by using a distance measure between the section and the observed data point. Choosing a section in data space is more easily thought of as choosing a point in the reduced space of the conditioning predictors. We could just enter values for such a point with the keyboard, but in high-dimensional space it becomes rather difficult to choose points that are anywhere near the observed data. It is more practical to use data visualizations which give us some impression of the distribution of data in the space, and click on them to select a section. Of course, we can just use a univariate display for each conditioning predictor, but selecting sections while only taking account of the marginal distributions of the predictors can result in many sections with no data nearby. The basic histogram and bar plot should be familiar to most OR users as the default plot methods for numeric vectors and factor vectors. We show the currently selected values highlighted in color usually. Bivariate displays offer a little more by giving a sense of the bivariate distribution of the data, allowing us to avoid some accidental extrapolations. The standard bivariate displays in OR are the scatterplot, boxplot, and spine plot, which is also known as a segmented bar chart. So the advantage the bivariate plots give you is that there are some values that may be well within the range of both variables, but are extreme values in the bivariate sense. So on the scatter plot, that would be somewhere like here, or on the box plot, somewhere like here. We can also see from the spine plot that there is one combination of the factor levels that has not been observed, namely cylinders equal to 8 and Vs equal to 1. The full scatterplot matrix shows every possible bivariate pairing. Factors are converted to integers for the purpose of maintaining the same coordinates across each plot. It would get messy putting box plots and spine plots into the matrix format while also trying to show the chosen section clearly. Generally, this is overkill and not very easy to use. The final option, parallel coordinates plots, these may not be familiar to everyone. Basically, instead of orthogonal axes, as in the familiar XY plot, axes are placed parallel to one another, and points are shown as lines joining the appropriate coordinates on each axis. As such, our chosen section appears as a single curve across the plot. This can be a useful visualization if there are a large number of continuous predictors, for which high and low have some meaning. It is not good for representing categorical predictors. This is a summary of the types of sections we can visualize by the type of response and the types and combinations of predictors we're investigating. We have seen one of these already. The sections we use have not really been finalized yet, so they may be different in the current version of Convis. For example, you see two blanks here. The reason for that is for logistic regression, we can show the estimated probability of belonging to a class, and so it behaves much like a continuous response. Whereas for some kind of black box classifier, we may only have fitted class labels, and so a basic color map might be more appropriate. So far, we've talked about choosing a section and displaying the fitted model, but we did not discuss how the observed data were displayed. How do we decide which data points to show? How do we decide what is near the section? So in trellis, intervals are used to decide what data points are plotted. This is a nice, interpretable way of conditioning on variables, but it is not very flexible and is most likely inspired by the need to create static visualizations suitable for printing. Instead, we consider a single section and use a distance measure along with a threshold distance to decide what points are plotted and how. A small example is the quickest way to describe this. Say we want to produce a plot conditional on x1 and x2, given x1 is 0.4 and x2 is 0.4. It's unlikely we have any observed data right on this point, so we'd like to see points which are nearby. So we visualize points within some given distance, giving more prominence to the points nearer to the section. So we currently implement two special cases of the Minkowski distance, the first being Chebyshev distance, which is the limit of the Minkowski distance as p goes to infinity, also known as the L infinity metric. This distance gives the kind of conditioning by intervals that you get in trellis. We also have the more familiar Euclidean distance, which is Minkowski distance with p equal to 2. Distances are calculated after scaling the conditioning predictors to have mean zero and unit variance. Let's look at another example. The next dataset we'll talk about is from a power plant. The data come from this Tufekci paper in a power and energy journal, where various machine learning methods are used to try and explain the data. Despite fitting these complex models, there is not a single visualization in the paper describing the fitted effects of a predictor. This is a case where the underlying processes are well understood, but involve difficult computation of differential equations in order to model them. So a flexible statistical model is preferred. The response is electrical power output, and the predictors mostly relate to the environment of the power plant. There are just under 10,000 observations in this dataset. Okay, so let's start with a fresh OR session. First, we include the convis package. We include E1071 for fitting support vector machines and MGCV for fitting additive models. We load the data and we can plot it to have a look at it here. So that's just a quick overview of the data. Okay, so we're going to fit two different models here and just put them in a list. So in the paper, they were fitting machine learning type models like a support vector machine, and I'm just going to fit a GAM here as well to kind of show the differences and similarities between the two. So we can start looking at some sections here with the CE-plot function. So this is just the support vector machine. So we can look around the data space and see how the model fits the data. One thing you notice is it seems like the curvature of the model changes a lot throughout the data space, implying interaction between the predictors. But one thing you'll notice is a lot of the curvature is kind of occurring in areas where you're seeing no data near the section. It's like this. This demonstrates the importance of showing the observed data. Otherwise, if we were looking at these sections without it, we might be tempted to place far more importance on these areas of high curvature, which are really just an artifact of the fitted model rather than the data itself. Okay, so let's bring the GAM in as well and we'll see what they look like together. So this is quite interesting. The GAM here that is fitted with a lot less computational difficulty is actually fitting the data quite similarly to the support vector machine. You'll note that the GAM is the same curvature in every single section here because that's the constraint of the additive model. And it's actually fitting the data in quite a similar way, and it only really differs in places where there is no data, such as here. Or this is kind of a strong example where it's a fairly wild extrapolation. So that's interesting. By looking at the sections through the fitted models here, we're actually seeing, by showing the observed data, that in the relevant parts of the data space, maybe these models aren't actually so different. And the real difference between these models is their extrapolation behavior. We saw earlier that we could have two predictors of interest and still produce a useful visualization of the section. So let's add vacuum pressure into the mix. So now our section has become a perspective mesh plot, and this is essentially the effect of ambient temperature and vacuum pressure on the power output given these conditions over here. So we can do the same thing. We can take sections, and I have added sort of residual bars to the observed data points here so that you can get some context as to where they actually are in the three-dimensional space. We can rotate this as well to get a better look at it. The rotation is not so smooth on Macs like this, but it's better in Windows. So we can get a nice kind of impression of how the model is fit. And one thing you see here is that a lot of this fitted surface that we can calculate because we have a function is actually not really relevant to any observed data. The observed data is kind of on a small strip up the middle of it. And this is kind of a well-known problem in statistics, but it's rare that you get to see it so clearly. This is the support vector machine, just in case I didn't mention that before. A quick summary then. We have introduced the condvis package for visualizing sections in data space. The real value of this software comes from being able to visualize and interpret black box models in high dimensional space. We then have a novel approach for showing observed data near the section according to a distance measure, so we can get some impression of how the model actually fits the data locally. The limitations are how far we can go in terms of dimensionality, picking sections interactively as we do is probably limited to around 15 or 20 predictors. The condition selector plots would start to take up a lot of space on the screen, and finding useful sections gets increasingly difficult. For categorical predictors with a large number of levels, the bar plot and especially the spine plot used for conditioning predictors tend to get a bit messy. Where else can this work lead? Choosing good or interesting sections can be quite difficult, so it would be nice to write an algorithm to find good sections to visualize. Then we could order the sections and visualize them one after another in a kind of conditional tour of the data space. In order to arrive at a selection of interesting sections, we could employ what Tukey called cognostics. This is basically having the computer look at a huge number of plots and selecting a subset for a human examination according to some criteria. So we could get the sections we want to see without having to actually display and look at all of them. There is then the inverse problem. What we've done so far is taking sections and seeing what the model is doing there. It might also be interesting to search for sections which have a given property, such as parts of the predictor space that have a certain range of fitted values or curvature of the fitted model. So far, we have been considering quite a strict interpretation of conditioning on single values. It might be interesting to see what can be done about conditioning on regions of the predictor space. This could be useful in instances where we're interested in the conditional effect of a predictor given some uncertainty in the other predictors. This will most likely involve estimating integrals of the fitted model. Finally, we have limited scope for model comparison in the current approach to visualizing sections, especially with the three-dimensional sections. It would be nice to provide for more model comparison in these methods. And to wrap up, here are some of the papers mentioned throughout the presentation. Okay, thank you for listening. If you have any questions or comments, please feel free to email me at the address on the first slide.